So today we're going to look at another example of creating a linear regression, or not necessarily a linear regression, a regression model using the library of functions we've studied this year so far to fit this situation. So this one I kind of fabricated or made up myself, but it's made up to fit like a real situation in history. So I was looking at carbon emissions, thinking about global warming. So I said carbon released at a location, a certain special location along the Amur River, because I wanted to work some geography and politics in here and a little economics. Anybody heard of the Amur River? I'm surprised every year that no one's ever heard of the Amur River. Where is this? It's in Asia. It's one of the world's most prominent rivers because this river is actually the border in East Asia between China and Russia. It's a very big river. It's where Siberian tigers are from. That's where their habitat is, pretty much. So it's a pretty important area in the world to know about. Anyway, so this is China, Russia. The part of China it is in is called Manchuria. Okay. So anyway, I was just thinking about that region of the world when I thought about this. So I said from 2000 to 2005, we're looking at a certain amount of carbon released in tons per day. So let's just scatter plot that and see what we get. But before we do the scatter plot, you guys need to help me think about something a little bit. How are we going to handle this mid-2011? 2001, I should say. 2001.5. Great. Also, these are all really large numbers that are close together. When you throw numbers like that into your scatter plot, it will lead to unstable models that are created. So there's a much better way to do this that you avoid having to know more mathematics with like heavy scientific notation and such. 2000 or 2001, either one of those you could make the year 0 or the year 1. You can change the frame of reference here, yeah? How about we just make it as easy as possible, and how about we say the year 2000 is 0? Okay, so let's write that down. For our scatter plot, we're going to say the year 2000 is 0. So over here, x will be years since 2000. If you do that, it will save you a lot of trouble on certain problems. Okay? So let's create a new scatter plot. So I'm going to go to my scatter plot and put in not 2001.5, but 1.5, and 2 for 2002, and etc. I think I went to 4.5 there. All right, so now I'm going to put my carbon in list 2. I think it's pretty clear on this example that X is going to be the year, and Y, we're looking at how much carbon is produced, so we're going to make it Y. Okay, now you guys flipped your lists in your scatter plot a second ago if you were following along with me, so let's make sure those are good to go. Right now list 1 is X, list 2 is Y. Let's make sure we're good on that. So mine says list 1, list 2, make sure yours does. Yeah? Might have just flipped it with me on that previous example. Okay, so now I'm going to scatter plot it. Zoom 9. And there is the scatter plot of this data. Okay, so now, looking at the shape, what kind of shape do you guys think we should try? I thought we'd try at least 2 different models. Exponential. Our library of functions is a bunch of shapes that we should know. You guys have about 6 or 7 shapes you should know, and those are things you should know for the final. They'll be all over it. What's the shape of a parabola? What's the shape of an exponential? What's the shape of a logarithm? What's the shape of absolute value? What's the shape of x cubed? We've got about 6 or 7 from now. Courtney said, hey, that looks like exponential growth. Yeah? I think she's right. What would be another good model option? We'll do exponential for sure. What would be another good option? What else might work here? Quadratic. I think quadratic might work here as well. The only thing that makes me a little hesitant to try quadratic is quadratic has a U shape, right? So it'd be good over here, yeah? But wouldn't it like start coming back up over here symmetrically and kind of mess up that spot right there? That's a good idea, though. That'd be a great idea. I'm thinking of one other function which might do a little better job than a quadratic. Anybody else? Courtney, I'll let you go in a second.
Linear, you could pass with linear.
Linear? This is like totally curved, though.
It may not be as strong as an R, but it will still, you get a good slope in there.
I think this is clearly curved, so I'm not going to do linear. I don't think so.
I forgot the function's name, but it was the S.
The S shape, the snake shape. That was x cubed. I think x cubed does this, doesn't it? I think cubic might be another good way to go. Quadratic's a great thing to try as well because it's clearly curved. So all three of those would be good. Let's just do an exponential and a cubic curve. So we go stat, calculate. Do you see one of the options we were talking about there? There's the cubic regression, right? Let's do that one. Cubic regression. Make sure it says list 1, list 2. I had the menu pop up on that previous example. Some of you have that, some of you does this, right? So I'm going to say list 1, comma, list 2. And it'll do a cubic regression for me. Whoa, that's a big, long model. So here we go. I'm going to write it out. So I'm going to put that down here so I have space. So one of my model options is y hat equals 823.77 x cubed minus 6289.761 x squared plus 15288x minus 11694.76. And on that one I have an r squared of really good, right? So a cubic curve explains 97% of the variation that we're seeing here in carbon emissions. Awesome. Most times in the real world, you don't get something like that, but remember, I fabricated this. Did you do cubic or did you do quadratic? Okay. So, and we'll have plenty of time for you guys to work out your things. So that's one option, okay? Let's look at our exponential option and get that one. So exponential, stat, calculate. You guys see anything that says exponential regression? No. Not yet, so maybe we should scroll down.
Yep. 0.
There's sine wave regression, there's logistic regression. We'll look at those in another class, or maybe this year at the end. Power regression is any generic power function, any x to the n. We're going to avoid that one for now too, though. What do you think this one is? ln. ln means natural log. This is a logarithm regression. I think you'll find that in another video I made if you'd like to see that one. But this is the one we're looking for, the exponential regression. Okay. So let's go ahead and pick the exponential regression. Right there. List 1, list 2. And there's our other option. So this option is a model of 0.2317 times 8.3457 to the x power. I'm going to write down its r squared while I'm at it. It's going to be 0.9778. I should have written this one down a second ago. Did anybody write this out further? What was it? 0.97. I could just do it again. It's pretty easy. Let's see. 9727. Okay, so both of their shapes are appropriate. It's appropriate for an exponential shape or for a vertical snake shape and a cubic shape. Does r squared give us a way to choose? They're both super good, yeah? But technically, if we want to pick the better one, which is it? Option 1, the red one. Slightly better. Either one of these would be great. So now, like on your exam, you're going to be asked to explain which one you chose. As long as you talk about the shape and you talk about r squared and you make a logical decision, it's going to be fine. Like on this one, this is totally a good way to do it. This is totally a good way to do it. We might have tried Riley's parabola. I don't think the shape on that would be quite as good, but I bet r squared is also pretty good on that one. You guys know what I'm saying? So there's lots of right ways to do the problem. So let's use our red model, though, to answer the questions they asked. So we'll just get rid of this guy for a second. Okay, so let's make a prediction for 2006. So here we go. I'm just going to type it in my calculator. 0.2317 times 8.3457 raised to the 2006, right?
No, 2000 is 0.
2000 is your 0. This should just be 6, right? Okay. So, for 2006, we're going to say our model predicts 78,289 tons per day of carbon released at this location in northern China. Crazy, right? But it's going up quite a bit. So, if I do 2017, I'm going to put in what? 17. Whoa! 1 something to the 15th power. 3rd power is 1,000. 6th power is whatever power is a 10. These are very important things to know. 3rd power is 1,000. What's the 6th power of 10? Million. 9th power of 10 is billion. 12th power of 10 is trillion. This is a number we probably haven't even heard of. 15th power. That's crazy. Now, global warming does involve large amounts of carbon, but you should still be skeptical when you make that prediction. Why is this not a good prediction?
Extrapolation.
It's extrapolation again, right? 2017 is way outside the data that we have available to us. So let's just think about what might be happening in this situation economically. Northern China during the period 2000 or 2005, along with much of China, was becoming more industrial. There's more factories, more coal-burning power plants. Maybe that's what's creating this amount of pollution. Maybe it's a highway from all kinds of cars. That'd probably be more relevant today. If this was an area in China today that started to surge upwards like this in such a short period of time, I would guess it's probably because of a highway or something like that, because China's developing more and more and more vehicles. They're actually developing their own automotive industry now. Their industrial growth has slowed some since it was early 2000s. But anyway, all those things could be happening, but it's key that you understand, even with none of that knowledge, this is far beyond the data range that we have, so we can't trust it. In fact, our scatter plot, probably after this, starts to do what? It probably starts to level out. I'm guessing it'll do something like this, because you can't just have this go on infinitely forever. Okay? So there's a good example. So we're going to say this is a dangerous, we can't make this prediction because 2017 is far beyond our data range and is hence a dangerous extrapolation. This is the kind of stuff I'd expect you guys to write on that worksheet and on my test if I asked you to do that. Okay? Last question I think for this one was interpret R squared. I just want to do it one more time for you guys. So R squared for this model, 97.78% of variation in Y. So in carbon emissions, I'm going to say, you can say tons per day if you want, can be explained by variations in the year since 2000. You could also say that, another legitimate way to say that is 97.78% of variations in carbon emissions can be explained by R exponential. Okay? And the cubic model would have done just about equally a good job. So you could have picked it as well. All right, I'll see you next time.